Hello, welcome back to my channel, and in this video we are going to learn about inner products. Okay, so let's first talk about what is inner product. So in 3D you have two type of vector products. One is cross product and one is dot product. The idea of linear algebra is to generalize the idea of a ordinary vector, and you also want to generalize the properties of this ordinary vector. Not all the properties, some of the properties that you can safely generalize. You cannot generalize cross product, we can generalize dot product, and the generalization of dot product is known as inner product. And now we're gonna see how do we generalize the notion of dot product. So what I'm gonna do, I'm gonna compare like all the things we have in ordinary vectors and then try to generalize in. Let's review the properties of our dot product that we have seen in calculus classes and try to generalize those. So what are the features of dot product you have that we want to generalize? Imagine you have two vectors A and B. Okay, so one of the thing we have in this dot product that this is symmetry. Second is that A dot product with A is greater than equal to 0, and this is only equal to 0 if A is equal to 0 vector. And the third one is linear, like A. Imagine you also have third vector A dot product with some combination of this B plus C, and you can B can come out, so you can take dot product of like this. It's linear like this, so this is linearity. And second one is called semi-positive definiteness, something like that. So these are the kind of the main feature of your dot product is, and we want to try to generalize. And the way we generalize this, let's now see how do we define all these things in vector spaces. Imagine you have vector alpha, vector beta, and vector gamma. Okay, so the first property is that alpha beta is a conjugate symmetry. Okay, this is not same as the first one, but it will make more sense after we learn about the norm. Why do we want this conjugate symmetry in our inner products? Okay, if you are trying to generalize from the above, you could have thought that alpha beta is basically beta alpha, but this is not true when you have complex numbers. So you need to be careful what we are defining here. The way we're defining this is because we want this alpha to be, if they both are same, we want our this when you're conjugate when you are taking an inner product with itself, the conjugate should is equal to its the inner product of itself should is equal to the conjugate of its own vector. And this is make sure that this when you're taking inner product with itself, it's real, because we define this thing to be a norm of the vector and we want it to be a real thing rather than which come at the notion of length, and you want length to be a real number, you don't want it to be a complex number. That it is greater than is equal to 0, and it is 0 only if is equal to this vector is 0. This notion of linearity and this would become, yeah. So the way we take dot product is I will talk more about this. How do we take the dot product? We are not defining any kind of rule how to take the inner product, but the way it's represented is like this. You're taking this is the inner product, but I haven't defined the rules how to take the inner product. Okay, but just to be sure you get so these are the property we need that your inner product should satisfy. So one of the thing we have norm or length of a vector. So now we're gonna define the norm, the length of the vector. How do we define in inner spaces? Okay, so if you have in your 3D geometry, you have, if you wanna define the length of a vector, you define it like a dot a, and this is how we have been defining length in 3D geometry. And the way we define in our inner space is something similar, that is alpha. Okay, so this is a norm of a vector, and a unit vector, and a unit vector is basically whose norm, whose length is 1, and then okay, and if the inner product of two vector is 0, is called orthogonal. So if we want to combine this notion of this normalization, and it's very common to combine the notion of this unit vector and the notion of orthogonal, and I will explain why. So if we have this okay, so the idea in even in your 3D dimension, we want a set of orthonormal set which are normalized and orthonormal to each other. For example, you have I, J, and K. So the idea is even in your 3D geometry, you have this idea of having a orthonormal set which are orthonormal to each other, which are orthogonal to each other, and they are normalized unit vectors. And the idea is that when you take this dot product, if you have orthonormal bases, then taking a dot product become very easy, and I will explain why. And in this one, the way you represent this orthonormal set is by this taking the inner product, and this is called this symbol is known as Kronecker delta symbol. And when I and j is equal to when I and j are same, then this is equal to 1. When I and j are not same, this is equal to 0. This is making this normalized, and this is the easy way to write this normalized and orthogonal set. So if I and j are not same, then these vector need to be orthonormal, which means the inner product need to be 0, and when you are taking inner product with itself, then the norm should be 1. So this symbol is generalizing that notion of orthonormal set. And the idea here is that in 3D geometry, you have this I, J, and K. These are orthonormal bases, and having orthonormal bases make it very easy to get the dot product and do other things, calculate the norm and get the component of other vectors. This algebra become very easy when you have orthonormal set. Dig a little bit deeper into that, why that is the case. So now we're gonna define how do we actually calculate the inner product, which is similar to how you calculate in 3D. So imagine this. Okay, so imagine you have these two vectors. How do we take the orthonormal? How do we take the inner products? And the way you take the inner product, we know this is how we take the inner product. But what exactly this thing is? This thing is basically, this is the dagger operation, and we will learn more about this. But for now, you just need to know what this dagger operation does. This is, you take the transpose and take the conjugate of those vectors. By taking the transpose of your column vector, that become this horizontal, and you're gonna take the conjugate of each value, and this is your and this become your this bra vector. We will talk about cat and bra notation a little later. The way you will define this dot product is basically, okay, so yeah, this makes it very easy. So if your basis in which you're writing your vector is orthonormal, then dot product become this. And if your basis is not orthonormal, then your inner product would not be very neat. And so it's always good to have your orthonormal basis. So whenever you have, which we will do later, whenever you have a linearly independent set of vectors, then you can always create a normal basis. This is using some Gram-Schmidt procedure. You can always make a linearly independent set of vector and orthonormal and make them orthonormal to each. So we will do that in a separate video. If we have this norm, the length they were defining, this is become the norm square, and this is, yes, so this is something you have already learned, and in the next video we will try to define more properties of this normal, this inner product. How do we define angle, and what is it?